Team 11212 the Clueless, and in this robot explanation video, we'll be going through our overall robot design strategy as well as the individual components.
What we're going to talk about is our overall robot design, or how we decided upon this overall design. So firstly, just to explain overall how the robot works, we begin with our double intake in the front. So I'll explain why we have two in a second, but we have two drop-down intakes to collect freight. We only use one at a time though. So if we're using this one, we'll collect the freight. It'll flip up. And then we have this deposit right here. The intake will shoot the freight into this deposit. And then if we're scoring on the Alliance shipping hub, then the deposit and the linear slides will shoot out. And then we'll dump it into the hub. So what that allows us to do is if we look at the actual Freight Frenzy field here, our robot only has to drive in about like as much into the warehouse as is needed to grab a freight. Then we drive out just a tiny bit out of the warehouse, and then our linear slides shoot out sideways. We can deposit the freight, and then we just repeat that over and over again. So that's how we score on the Alliance shipping hub. And on the shared shipping hub, what we do is on this side, our robot might be here and we use our left intake and our linear slides go that way. When we're scoring on the shared shipping hub, we use our right intake instead. And then our linear slides don't extend very much, but they go kind of this way instead. And we score on this side of the shared shipping hub. So that's the reason for having two intakes, and that's how our overall design works. And then another key aspect of our design is that in endgame, we actually position our robot like this again, and then we once again use our right intake. And then we can score the ducts that fall off right here using our linear slides going diagonal once again. So that's the overall explanation of how our robot works. Now, why did we do this and how did we get here? One of the key aspects that defines a fast robot every single season is minimizing the amount of movement. So you want to be doing as many things simultaneously as is possible. So this year we minimized movement by only having to go in and out of the warehouse a tiny bit. That's literally as less movement as you can possibly get given the rules. So we just go in, grab the freight, come out, and we do that and cycle like that. So that's how we get such a fast cycle time. And in general, linear motion is always faster than something like rotational motion. So in order to actually get the freight from our robot against the wall to the shipping hub, we have these long linear slides. And these are able to shoot out like up to 5 or 6 feet in maybe less than half a second. So using linear slides like these is almost always the fastest way to get motion. And then the last key aspect of our robot is that we don't have to even wait for the linear slides. While our robot is driving out of the warehouse, we shoot the linear slides out at the same time. So by the time we're already out of the warehouse, this whole mechanism is ready to deposit, and the drivers just have to make some minor adjustments in the linear slide and turret position. And this is true while going back into the warehouse as well. We don't have to wait for this to retract, we just do it at the same time as our robot drives into the warehouse. So we took, about 4 weeks at the beginning of the season thinking through all the aspects of the game and trying to optimize for time. And that's how we came up with this design that theoretically maximizes everything. At the same time, there's a lot of designs that can achieve the same thing. For example, in the beginning, we considered designs similar to technical difficulties or brainstormers, if you know what their design looks like, in which we have a similarly thin and long robot. We have two intakes as well on opposite sides of the robot, and we have linear slides that either go out horizontally or are on a turret and can go in a variety of directions as well. One of the reasons we actually went with this design, first of all, we really wanted this turret that our linear slides could go out diagonally, once again, to optimize our cycle time and minimize the amount of distance the robot has to drive.
It was to make the transfer system much easier, because otherwise if you have to transfer systems on both sides of the robot, it takes up a lot more space.
That is true. So yeah.
I don't know, if you just look at the front of the robot, the transfer is basically it takes up basically no space.
Okay. Another common and popular design that you definitely see a lot is a simple pass-through design. So with that design, we just have the robot like this, let's say we have one intake in the front right here, and then we just have an outtake in the back. Maybe if this is a top view, I'll draw like a side view here. We have the intake in the front right here, and then we have like maybe some slides going like that and like a virtual 4-bar, or maybe we have another set of horizontal slides. That's what the team that ended up winning Worlds actually did. And this is definitely a fast way that we recommend for teams who don't want to build as complex or ambitious of a robot as ours. But once again, we really wanted to minimize the amount of distance the robot has to move, be able to do as many things simultaneously at the same time. And we thought this design had more potential, and still, with like a 10 freight auto, we think it does. What's really important is thinking of tons of designs at the beginning of the season. We spend a crazy amount of time just brainstorming before we begin building anything. And that's to achieve what we think is the optimal design. Alright, so now we'll talk about how we kind of organize our season and how we actually progressed from nothing to this robot. So as I mentioned before, we spend about 4 weeks in what we call the concept phase, where we're just brainstorming robot design ideas, theorizing how fast each of them will be, and then eventually deciding on one. Throughout that process, we also do a lot of really detailed drawing. So we make sure that our vision is actually practical. We look at all the dimensions. Is it possible to actually fit all those mechanisms into the limited space that we have? So the first 4 weeks of our timeline is spent on the concept phase. The next phase is the prototyping phase. So this is where we take a deeper look at specifics of every subsystem. So for example, we started looking at specific intake designs, whether it be better to go with like a surgical tubing design or something else. So we build specific subsystems for maybe 2 weeks and test them out and decide on, more specifically how we're going to do everything. After that, we go into our simultaneous CAD and build season. So this is where we start designing the final robot design in CAD. So we always start with the drivetrain basically. We maybe CAD that in a week and then we build that the next week. Simultaneously, while designing the drivetrain in CAD, we'll start working on the other systems. So after that, we began working on designing the first iteration of the intake. Based on our prototype, we basically make whatever improvements we see fit and then slap that on the final robot. And then while we're building the intake, we'll start designing the turret and linear slides and so on. So we have kind of this process where we simultaneously design and build the robot. And we think that's just the fastest way to do things. Sometimes we'll make mistakes that we need to go back and fix later, but that is fine. So we actually only spend about 6 to 8 weeks on the entire CADing and building season. And then after that, we have a few weeks for software to program the robot before the first competition. So you can see in our scrimmage in like December, we already had a robot that looks almost identical to this. Of course, by that time, we were averaging like 40 points every match. And that's what takes me to our last part of our season timeline, which is what we call the optimization phase. So this is where you get from a robot that looks cool to one that is able to win. So we spend like 15 to 20, maybe more weeks just testing and optimizing the robot. So we have a spreadsheet where we've run thousands of cycles and we track what goes wrong every single cycle. And we brainstorm, review footage, and figure out how to fix every single one of those bugs. And that's how you go from a really complicated robot that doesn't really work well and looks cool to one that will actually perform well in competition. So it's really key that you spend a really large amount of time on testing and optimization. And that's also how we train your drivers.
We have a 12-inch wide drivetrain, and that was a design choice to fit between the barrier and the wall on the field. And then we have, to accomplish this really thin drivetrain, we have a parallel plate design where we sandwich the wheels between 2 plates. We also decided to go with mechanism wheels so that we could be able to strafe and maneuver around the field and in tight spaces like the warehouse. We have Neverest 20-to-1 motors that are in the center here, and then they go to this belt which is attached to the wheels, and so that is how the powering works. Additionally, we have odometry pods, which are dead wheel, and so they're also liftable, and they have springs to come back down, and so that allows us to go over the barriers, but we can also have localization during autonomous when we are just going forward and back and not going over the barrier.
At the beginning of the season, we decided to go with a thin drivetrain. So in the strategy phase, we were brainstorming several drivetrain designs to be able to go over the barrier as well. But just from a physics perspective, we decided that no matter what, going over the barrier would always redirect some of the robot's momentum upward, which means you're losing momentum that's horizontal. So we thought that going around would always be the faster option, but we also built in the capability of going over the barrier as well. So our drivetrain plates are kind of curved up right here, so we do have the capability to go over the barrier in the case that another team blocks the opening. And another fact about the drivetrain is that we use a dead axle design. So what that means is that this wheel spins right here, but the actual axle the wheel spins on is bolted into the drivetrain, so the axle doesn't spin. So it's actually an 8mm Rex axle from GoBuilda that is screwed into each of these plates, and then we have bearings around the actual wheel that allow the wheel to spin around the axle. And then once again, it's just powered by these belt systems. So I would say the main advantage is just packaging. It's more compact. So if you have a live axle, then you would need bearings on either side of the drivetrain plates to allow the axle to spin around the bearings. So those bearings take up more space here or there. And then you also have to constrain the axle horizontally to make sure the axle doesn't come out. Overall, it's just a lot simpler to just bolt the axle into the frame. And it also provides additional support by holding everything together. So as Toby mentioned a little bit earlier, we also use 20:1 gear ratios on all 4 of our motors. And the reason that we chose this is, firstly, 20:1 we think is a pretty good balance of speed and acceleration. Our robot is like 40 some pounds, I think, in the light 40s or maybe high 30s. So this heavy robot requires a lot of torque to be able to accelerate quickly, and it also gives us a decent high speed. So that's why we chose 20:1. If you have a lighter robot that's like 20 to 30 pounds, we think it might be better to go with something like 15:1 or 16:1. But for a heavy robot, we chose these motors. In addition, you can see our motors are mounted kind of as back and as low as possible. So we will always want to keep a low center of gravity. That makes it harder for our robot to tip over, and also makes it easier for us to strafe and accelerate because it's just very stable. And then finally, you can also see that the bulk of the stuff is in the back of the robot. That design choice was kind of just because we anticipated we'd have more things going on in the front. For example, we have our intake motor, although to be honest, not that much else. So we just kind of designed in the back heavy to begin with so that we'd have more opportunity to build off the front.
So looking at the odometry for our robot, we have 2 vertical pods and 1 horizontal. These are all able to be lifted so that when we go over the barrier, we don't destroy our accuracy or the odopods themselves.
To clarify, there's a string that was attached to the servo horn here and then went through the Teflon tube, and so it was attached down here, and then the string would slide through the tube, and when the horn was moved up, it would pull the odometry. So this Teflon tube here is fixed, and it's the string that moves, it slides through it to lift the odo.
Also, just generally, our odometry design is based on open odometry released by primitive data. So you can see it's modified in several ways. We tried to make it as thin as possible because we have this really compact drivetrain design. In fact, it's kind of suboptimal right now. But and the reason we actually made it all metal is that we didn't want any flex, because for your odometry, it's really important that it can't flex up and down. Or you'll lose accuracy. So that's why we tried to make it out of metal to make it as rigid as possible.
Editor's note, using metal odometry was probably a mistake for this season. The fact it was made out of metal meant it was really hard to remachine it and get a new one quickly. And then also, when we were originally manufacturing them, we decided to take a file in order to make sure that the bearing could fit in on all of the odometry pods, but that caused wiggle, so the odometry pods could wiggle, which meant that they're not as accurate as they could be.
But we used these 35mm wheels from
Rotocaster.
Yeah, Rotocaster Omni wheels, and then we use the Rev encoder. And the reason we use such a small Omni wheel is just to make the module as compact as possible, and the Rev encoder is just the simplest and easiest to use.
To hold this wheel in place, we have a 25 millimeter shoulder screw going through the wheel and down under the Rev encoder, and there's a nut on that side. And then to support the distance between these two metal plates, we have a 3D printed part with a hole that we're able to lift or string the odometry to lift it.
And finally, to actually mount the odometry pods, it's also very important that these are, the mounting point is not going to flex itself. So we mount the odometry pods in two different ways. In the vertical pods, we have these standoffs that go through, so they're screwed in on both sides, and this whole drivetrain assembly is very rigid. So we're not afraid the standoff is going to move. We actually have a cantilevered odometry mounting right here, which means that it's only supported on one side. But the way we are able to achieve this is we use this really beefy design where we have two clamping hubs on either side of this channel, and then a standoff going through that. So there's a really thick mounting point right here. So we're not worried about this flexing at all either. And then lastly, the odometry needs to be sprung into the ground. Otherwise it's not gonna have very consistent contact. So maybe the best example of springing is right here, where we kind of just have this horn going upwards, and then we pull that towards something else, and that springs the module into the ground. We're going to talk about the actual structure of the drivetrain and how we, build all of the structure of the robot, basically. So starting off from the drivetrain, you might have noticed we use these two Actobotics channels to connect them together. And you might also notice on this inner plate right here, both inner plates of the drivetrain have this kind of gridish pattern. And then if I flip the robot onto its bottom again, you might also notice that we have the same hole pattern on the top of the drivetrain. So our team is mostly Actobotics based. The reason we don't use GoBuilda is primarily because we have more Actobotics stuff already. So we just use what we have. But putting this grid pattern pre-drilled into all of our drivetrain plates allows us to really easily build off of it. So you can see we build off of the channels in the drivetrain a lot here and also in the front. And then using this hole pattern here, we're able to mount the plate that holds our turret in place right here. We're able to mount things like this side wheel. And then we also mount just real Actobotics parts to it, like this 90-degree bracket right in there. So creating this nice hole pattern in your drivetrain makes it really easy to build off with the rest of your robot. At the same time, you can note, it's probably pretty obvious that a lot of our robot is CNC machined. So that's definitely probably the most useful manufacturing method that our team uses, is we design it in CAD and machine custom parts. But we do use plenty of commercial off-the-shelf parts as well. So I mentioned those Actobotics channels. We actually mix Actobotics and GoBuilda as well. So you can see a GoBuilda channel right here, which has a motor embedded into it. And then we use GoBuilda beams for other structural components, like up here is a GoBuilda beam. We have Actobotics beams running at the sides of the robot. Pretty much we mix all the build systems as we see fit. And being able to 3D print and CNC machine allows us to get all those weird metric and imperial systems to mix together. But we see advantages to both systems, so we pretty much just try to mesh them as much as possible. So, for example, the reason we didn't just put an Actobotics channel onto the side of this channel is because you can fit an entire motor into a GoBuilda channel. So that's why we chose a GoBuilda channel right here. But otherwise, we use Actobotics because we have that. So next we'll be talking about one of our specific subsystems, which is the intakes and transfer system. So from the very start of the season, we decided that since this game reused the game elements, which are those gold blocks and white balls, that we could easily look at past games and see what the best intake design was. So from very early on, we decided that we wanted to use a surgical tubing design because we'd seen from like Data Force and Gluten Free and Rover Ruckus that those were easily the fastest intake design. They were almost instantaneous. So that's how we decided to use the surgical tubing design. And then we decided on kind of this bucket that would just hold the block. And yeah, so I would say the two main challenges when designing our intake was, one, we want it to be extremely fast, and two, we don't want to grab more than one. So yeah, our initial design was kind of just a bucket with the surgical tubing roller. You can see we have now these 45-degree slopes. What that does is we found that our old design still sometimes could grab two of the freight. So what we did was we just prototyped and tested over and over, trying many different ideas until we got one that would consistently just grab one. And we ended up finding that these slopes work the best, so that's just what we went with. So we were considering two designs mainly in the beginning. The first is this bucket design, where we kind of just have this bucket right here, and then we have our intake roller right here with surgical tubing. So this would just fit one freight in here, and that's it. You know, it's pretty simple. After you get the freight, then let's say there's a pivot point right here. This intake would flip up, and then you would just reverse the direction of the intake, and it would spit the freight out. So that's the design we ended up going with. Another one that we considered was actually more like this. So we have another surgical tubing shaft right here, and let's say another one up here if needed, where we just send the freight up here, and then it would fall into some bucket right here, and then we just, after we have the bucket, or after we have one freight in here, there's not enough room for another one. So let's say there's another bowl right here, then we just start outtaking or reverse the direction of the intake, and it would shoot this back out. So we also only get one. And the main differences between these is just the method that we transfer the freight. So this is more direct. This requires flipping the intake up. We actually ended up going with a flip up intake because that was what we could package into our robot. So this takes up a lot more space, but with our current design, it might be slightly slower because we need to raise the intake, but we gain a lot, it takes up a lot less space. So looking back at our robot to talk about the actual transfer system, after we collect a freight, we will flip the intake up. You notice how this bucket is positioned here. We just flip the bucket up, and then we start reversing the direction of the intake, and then it just shoots the freight straight into the bucket. So this is an extremely short transfer design. Although we have to wait for the intake to move up, which is kind of slow, the transfer itself is almost no distance at all. So, when freight is moving through the robot, we also want to make sure that is as fast as possible. So that's why we went with such a short transfer design. Now to talk about some other specifics of our intake, again, we're trying to make everything as fast as possible and as consistent as possible. So we'll talk more about sensors later as well, but we have a force sensor inside of the intake. So once we have a freight in here, it'll press against this foam. We can detect that, and then after we intake it, we lift it immediately. And then, we shoot it out the back. Some other things that we do to assist the speed of the intake is, you might notice we have this spring system here that's pulling it up. So this pretty much negates a lot of the weight on the intake. So it's like kind of weightless, sort of. But basically the spring helps the intake servo pull this up all the time. So that also helps increase speed a little bit, at least in theory. And then finally right here, we're using a super speed servo with a chain right here. And the super speed, we tested, a torque servo, a speed servo, and a super speed servo. We just found that the super speed servo was the fastest, so that's what we went with. Super speed servo from Go Builder. And finally, to talk about the powering of the intake, we have two intakes here that are both powered to the same motor, but actuated by independent servos. So the motor is mounted down here. It's mounted low because, once again, we want a low center of mass so our robot is stable. So this just drives a thin belt that goes up to this shaft. This is also a dead axle design, so these pulleys spin around a stationary metal shaft that goes through the whole length. This pulley spins these pulleys, which go down to the intakes and spin the actual surgical tubing shafts.
We move to the turret. So the turret is important to switch from one intake to the other. And the turret functions with a bearing stack. And so there's a big bearing, a little bearing, and then another big bearing that rotates on this plate here. And so what this looks like, if you come over here, is that we have a big bearing, then we have a little one, and then a big one. And so these then are in a circle, and they ride along a plate that is on the little one. And so the two big ones support the weight of the turret, and the little one creates the rotation. And so the little one prevents it from sliding around inside the plate while the big ones hold it up. And so if we go back to the robot now, you can see that this turret, if I try to move it, the robot's moving, not the turret moving inside. And I can pick up the robot from the turret, and it is supported by that bearing stack.
And just to talk about the reason we went with this bearing stack design, it is possible to just buy turrets online or buy turntables or like Lazy Susans. We just knew that, first of all, these bearings are pretty inexpensive, and secondly, it's a proven method. So it's simple and it works and it's strong.
And as mentioned earlier, we mount the motor down here to keep a low center of gravity, and this is driven with,
So there's
if you look inside here,
there's a little gearbox in here that translates the rotational motion from around the motor to this belt here, and then
those are two bevel gears from GoBuilda.
And then the belt system is used to power the turret. And so we have just a giant pulley going around, and this gives us a lot of torque and fine control over the turret.
We always think it's best to power a turret using a belt system because it's super easy to 3D print this belt right here. It doesn't even have to be a very strong print because there's so many teeth that are in contact all the time. It's just easier to manufacture a belt than say a gear. And this belt has a lot of precision as well. But you know, if there is something we would change about our turret, it's that we use these bevel gears down here, which introduce a lot of play. So we're actually able to move the entire turret assembly a little bit without the motor moving. Part of that play is from an imperfect mesh in the bevel gears, and all the rest is just from the motor.
Idler is just made up of a screw and a little spacer on the top.
And so what the idler does is it pushes the belt in, and that makes sure that there's no play in the belt system, but there is still some play in the bevel gears.
So the next section is going to be on our entire linear slide system. So this is probably one of definitely the fastest systems on our robot and took a lot of work. So just to start off with the basic structure, we use these black 2-stage linear slides. They're 300 millimeters long from Long Robotics, and we think they're pretty good. They're really compact, they're smooth. The only issues we've had is one of them losing some ball bearings, but so far it's been okay. The reason we mount them in this fashion, I think we have 7 stages. Yep. And we have 2 sets of 7 stages facing each other. This is generally the most stable way to mount these 2-stage linear slides, is facing each other. Alternatively, we considered for a brief period of time having just 1 set of these linear slides, but if we're running 7 stages, you know, we lose a lot of stability by just having 1 set. So that's why we implemented 2 sets facing each other. The disadvantage of having 2 sets is, of course, it's heavier and it's going to require more torque to move. So that's the actual linear slides. In the middle here, we just bolt the 2 sets together with a channel because that was convenient. Now, to actually power this system, we began with just a one motor system, but we simply couldn't move that much mass at the speed we wanted with 1 motor. So what we ended up doing is switching to this dual motor system. So the 2 motors are just geared together, which works perfectly fine. We tested a lot of different gear ratios. We machined a ton of versions of this plate right here until we found what we thought was optimal in terms of current draw and speed. So we have these 2 motors powering this central shaft right here. This shaft spans across the entire set of linear slides right here. So we move it a little bit. Yeah, and then it spins these spools on either side. So that's how we determine this powering system. To explain how the stringing is done, you can see we have a set of 4 spools in total. We have 2 sets of spools to drive each side because we want we don't want it to be unbalanced, and if one side breaks, we want to still be okay. So one of these spools pulls the linear slides in, and one of them pulls the linear slides out. So in this case, the outer one pulls it out. So basically, you can see this string wraps on top, while the spool that pulls the linear slides in wraps on bottom. So this way, when we spin the spools one way, it's going to pull in one of the strings while it releases more of the other string. So that's how we can have the same shaft power the slides in and out. Now the slides are continuously strung, so this means when we pull the string, I'll draw this on the board, but basically we have multiple stages that look kind of like this. I'll draw them offset a little bit. So let's say the motor is right here with the spool. If we have a pulley down here, a pulley down here, pulley up here, and then an anchor down here. So we just pull the string around like this, and then we anchor it down here. So this way, when we pull this string in, we're actually pulling this string up. So, this slide is going to move up. Then once this end stop hits the end stop here, it's going to pull this stage up and so on. So that's how we're actually stringing the slides. When we pull the string in around the spool, it's going to pull the string up here and make the entire system go out. So that's the principle of extension. Once again, you can see that kind of zigzag design throughout our entire linear slides. We have the spool start right here, it pulls the string around all these zigzags, all 7 stages, and then it anchors right here on the last stage. And you can also see we try to put the anchor design, or we try to keep the string as straight as possible all throughout. So that way the forces are just pulling out. If there's a lot of diagonal or horizontal angle on the string, it's going to redirect a lot of the force into pulling horizontally. And that's inefficient. We don't want that. Now to talk about the retraction string, or the string that pulls these slides back in, this is a lot more simple. We simply have this spool right here, and a linear string that just goes all the way to the last stage. And so when the spool spins and pulls this in, it's just gonna pull the last stage directly in. And it happens to be that, the rate at which the string is released and pulled in is exactly the same. And so is the velocity of the slide. So we're able to put it on identical diameter spools right here. Now, a couple of challenges we had with stringing in the beginning of the season was that, these 2 lines would go slack after the slides extended for a long distance. And this is because basically not the perfect amount of string is being released. So let's say like more string is being released while we're extending than is being retracted. That would result in this string becoming loose. So a couple of ways we fix that is, firstly, we have these springs at the end of it. So these keep it slightly more taut. So there's always a little bit more tension. So that just kind of eats a little bit of the slop. But also, we switch to as thin of a string as possible. So when the string stacks on top of itself, so you can see the string generally here is like pretty sorted out. There's only one layer of string, but when the string overlaps on itself, then the radius of the spool effectively increases. So that means for every rotation of the spool, if it's layered on top of itself, it's going to be drawing more string than if it were just one layer. So the way we fix that was, number one, we make the spools as wide as possible. So there's more space to create a single layer. And then secondly, we use as thin of string as possible. So we're using some Kevlar line we bought from Amazon that I think is like 0.8 millimeters thick, and that prevents the string from overlapping. Finally, we want to make sure the string doesn't jump off of these pulleys. So if the string gets off of the pulleys and gets jammed, then it's going to jam the whole slide system. And this is a problem that we had earlier in the season. Now we fixed it. You can see right now it's jammed. If I just move it a little bit, it fixes itself. But the way we do this is basically just ensuring that there's a perfect distance between the bearings. So the bearing inside of this 3D printed yellow part is able to spin smoothly, but there's just not enough distance that the string can get caught inside of it. And the way we do this is that if I go onto the board, you have to make sure the 3D print is pretty perfect. So this is kind of what it looks like. The bearing is inside of here, right? That was a bad drawing. So, and we have a screw going through right here. So we got to make sure that the 3D print up here is a through hole, and the 3D print down here is is threaded. So that way we can, depending on how much we spin this screw or how much we tighten it, we can change how much this 3D printed yellow piece is clamping onto the bearing. So that's how we perfect the tension on all the bearings to ensure the string doesn't go off track. Last thing about linear slides is just that it's good to frequently grease them. We just use a silicone grease, and that makes them a lot smoother and faster. And then one more thing is that to actually stabilize the slides, one of the issues that we had was with 7 stages, there was a lot of sagging. And so once we got back inside of the drivetrain, this whole system would not be very stable. And so the way we fix this, inspired by gluten-free and also our relic recovery season, is we built a rail like this. So there's just a lot of bearings on here that are kind of on this rail. So once the slides come back in, you can see this metal channel here is going to contact the bearing. And once we go back inside, then it's in a very stable position for us to start transferring freight back into this bucket. So we kind of just added this additional stabilizer inside the robot for the slides.
So now we're going to be talking about our end effector and our depositing system. So we had originally started with a virtual 4-bar, and pretty much how this works is that this is stationary, a motor would be geared to here, and this would rotate with a timing belt. And how this would work exactly is that we would extend our slides out, we would go to a specific level on the Alliance hub, and then we would dump from under, so the mineral just drops, and this would allow us to maintain the angle between every single cycle. And we soon switched to this end effector, which is a much more simple design. And pretty much how this is mounted, there's a custom CNC'd plate with a servo block, and we use a Go-Build torque servo. And on the servo horn, there's a Go-Build beam with another CNC'd plate, and there's a super speed servo, which is attached directly to a 3D printed bucket. And we could easily rotate the arm and dump the mineral. And this was very convenient because it only used 2 servos, and it was very fast, and it was pretty sturdy as well.
The reason we switched to this design is because we needed to save a lot of weight. So this whole mechanism with the motor on it was extremely heavy, and adding more load that the linear slide needs to extend made the linear slide slower. And also when we were at full extension, we had severe issues with the robot tipping. So this whole design of the end effector is designed to be as minimalistic and as light as possible. Shared ramp?
And we also have this 3D printed shared ramp. You can see from this end, it's just attached with a few screws. And what this allows us to do is have minimal motion with our V4 bar, or our end effector, and the mineral just slides down the shared ramp and onto the shared hub. So all we're doing is we're getting a mineral from the front of the robot. We flip the intake up, outtakes into our bucket, and we have very minimal motion with our V4 bar, and we just dump this servo and it slides down.
5 seconds left. Take for 4, 3, 2. I'm going to talk about our 7th iteration Carousel Spinner. So the first important feature is that it extends a bunch, and so this uses a 2-stage passively powered cascading linear slide. And the reason that it needs to come out so far is because from the beginning we decided that part of our strategy was duck recollect and scoring while spinning them off the carousel. And so we needed this extension to get far enough away from the carousel so that we could drop an intake and use this flap so that when the ducks fall down, we can swap them into the intake. And so this flap here just increases the percentage of ducks that actually make it into the intake and don't bounce away. And so how the mechanism here actually works is that over right here, there is a constant force spring, which is extended out in the in position. And then when when this servo here rotates, it releases it, and then that allows the constant force spring to retract, and that causes the extension of the first stage here. And then this stringing is cascading, so it's attached back here to a fixed point, which is at the end of the first stage, and wraps around a bearing and then is tied down. And so that makes it so that as this first stage extends, the second stage extends. And so that's how cascading works. One stage here, and then there's this, and that's very thick. And so what you have is the string comes from here, it goes out over a bearing here, and then it's tied down, and so that makes it so that as the first stage moves, the second stage moves. And so cascading requires more torque, but it gives you, in this case, twice the extension, or you'll get as many more times extension from one stage of movement times the amount of stages that you have. And then if we move here to the actual powering system for the spinner itself, we have two super speed servos, which are geared together in a similar fashion to the linear slide extension. So there's two gears with a smaller one in the middle, and then we had to use gears so that each gear has the same amount of contact on that central gear, and that distributes the load of spinning it equally on both servos and makes them work together instead of fight each other. And so you can see that they both rotate the same direction, and that causes the rotation of this spinner.
Now let's talk a little bit about our sensors. On this robot, we currently use over 20 sensors, and starting from the bottom of the robot, we have 3 odometry pods, which we discussed previously. And then moving upwards, we have a force sensor in each of our intakes. And what a force sensor allows us to do is it will detect if a mineral has entered or has pressed this surface. And upon a trigger from this force sensor, we lift this intake, and we ensure that we have lifted it by using a magnetic sensor that is mounted right here with a magnet on the side of the intake.
So we faced a couple of issues in the beginning of the season because servos don't have encoders, so we don't actively know the position of our intake. So sometimes, when trying to transfer the freight, the intake would fail to move upwards because it gets stuck, and then we just spit out the freight, back into the field, which is not helpful. So this way, we're able to ensure that we only transfer the freight after we know the intake has gone up. So that's the reason for the magnetic sensor.
So after the magnetic sensor is triggered and we know that this intake module has raised, our turret would be rotated with our bucket facing this way, and the mineral gets spit out into this bucket, and inside of this bucket we have another force sensor, and again this is to know that the mineral has gone from our intake module to our end effector. And once this sensor is triggered, we extend our slides, which then dump and retract. So some other sensors that we have are 2 ultrasonic sensors, and pretty much we use these to look at the wall in front of us, and this allows us to increase our localization accuracy. And something to note about these is to make sure you mount them at the right height so that you actually see the wall and you don't get interference with the ground, other robots, or minerals. On the sides of our robot, we have a flex sensor, and again, this improves our localization accuracy. When this is flexed, meaning we are against a wall, then that gets triggered and we can know one of our axes of the robot.
But the webcam, we just run a TensorFlow object detection model to detect where our capstone or where our team scoring element is. Or actually we use April tags now, but this is just a small clip-on mechanism that goes like that.
And of course we use the IMU of these two hubs. One is a control hub and then the other being the expansion hub.
Now to just give a more broad overview of all of our localization methods, something that allows our 10 freight autonomous is having near perfect localization. So we've already mentioned we have 3 odometry pods. Those track our changes in position, every 6 to 8 milliseconds, which is our loop speed. In addition to that, we use these ultrasonic sensors to reset our Y position every now and then. And then we also use the flex sensor on the side of the robot to reset our X position or our horizontal position every time we ram into the wall. So this way we mitigate any X and Y drift. And then finally, every few hundred milliseconds, we'll also read from the IMU in the rev control hub, and that allows us to reset our heading every 100 milliseconds. So this way we have methods that are basically driftless in X and Y, but also are able to track accurately every 6 to 8 milliseconds. Okay, now we're going to talk a little bit about power transfer, basically how we get power from a servo or a motor to power whatever we want it to. So on our robot this year, we use a variety. We use gears, chain, and belt, I think. Those are the main types. So in general, we almost always are using timing belts because these are the fastest way. There's almost no friction. It's really simple. And it can go a long distance as well. So we use belts on our drivetrain, on our intake, on our turret, basically everything. In places where we use gears, in general, obviously the points need to be really close together, but gears are pretty good for, I guess, also frictionless travel. So if you ever have any really close center to center distances, gears are also a pretty good choice. And then finally, we use chain in 2 places, which is just on either of our intake lifting mechanisms right here. And the reason we use chain here instead of, say, belt is mainly because belts don't work very well at really small distances because, if you imagine a loop of belt that's really big, it's able to flex more easily into like a loop shape because belts are normally circles. We need to flex them into a loop for them to work as a powering system. But if you have a really small belt, it's really hard to flex that into a loop, if you can imagine that. So that's why we use chain in this case, because the center to center distance is kind of not very small, not small enough to use gears, but not big enough to use belts. Let's talk about servos and servo blocks. So our robot entirely consists of go build a servos. We use torque, speed, and super speed servos in various places. Except we have 2 rev servos because we just ran out of go build a servos at some point. But so yeah, basically we have a storage of all 3 types. We just pick whichever one is fastest in any scenario. But in general, go build a servos are the most inexpensive and strong and torquey servos that we've had. So we just use those all the time. We don't think there's necessarily a need to buy extremely expensive like Servos servos. And in many places, we will experience servos breaking a lot of the time. So this is why we use something called a servo block, like right here. So, if a servo is going to face a lot of torque in like this direction, or not rotational or axial torque like this, then a servo block is definitely a good choice. So it provides additional support out here by putting another bearing out here. So this way, if our V4 bar, if our end effector is out here, if someone punches it this way, the metal servo block is able to take the torque instead of just like snapping the shaft of the servo off. So it's pretty good to use servo blocks whenever you're gonna have torques like that. There are plenty of cases where we don't use servo blocks as well. Like you can see on our carousel system, these 2 servos don't have servo blocks. And this is because there's never gonna be that sort of non-axial load on the servos. They're geared to the central gear and likely nothing will collide with it. So there's no fear that anything is gonna snap the shaft off the servo. So in this case, we don't have to use a servo block.
Wire management is really really important both for functionality and aesthetics. So one thing that we've done in a lot of places is we've sleeved the wiring, and so we think this provides both a better aesthetic than ketchup and mustard, and it also protects the wires from getting pinched anywhere. And so what we've done with our wiring is we've gone through a lot of different ways to keep them tight together and also out of the way. So you can see here and on each side we cut holes in our drivetrain, and so this allows for us to get wires in and out of the drivetrain, and they're out of the way so that the turret can still rotate. So the wires go from the motors, they go out into the plates somewhere, I believe right there, cannot be seen, but it's between there, and then once they're in the plate they travel along and then up, so follow like the path of this Odo cable, and then once they are up in the top, we have a bunch of them going up to our control hubs, which are at the top, and this is because this is where there is space, so that's where the control hub and expansion hub go. We also have a coil cable here, and so this is a telephone cable that we cut the ends off and have replaced them with servo pins at the end. And so the coil cable makes it so that we can extend the slides, and it keeps it out of the way, but it's coiled so that it can extend. And this is one way of wiring over long distances. Something to note is that it essentially does act like a spring, and so when you extend it, it is pulling back the extension some amount. And there are some other ways that you could wire over linear distances. And then I think an important note with the coil cable is that there are regulations on the thickness of the wire, the gauge, and so I think we got this one off Amazon a couple years ago, and it satisfies the rules. Another part of the wiring is the battery mount. So in our robot, we wanted to put the battery kind of in a central location because it has mass, and so we have these plates here that are essentially just steel plate that we cut so that we don't tip when we extend the slides, and it just worked perfectly so that the battery fits in here nice and snug, and then we can plug it in like so. And so this just, the fuse sits in here, and then the battery sits in here, and then when the slides come in, it just covers up the battery. And so the battery is nice and protected, but it's also in a good spot for our weight distribution because it stays fairly central in the robot.